Thank you for coming today. I appreciate the opportunity to talk to you a little bit about geothermal energy and some of the work that we've been doing on the topic for a while. My name is John Holbrook. I'm a professor at Texas Christian University, and I recently led a group called SED-HEAT, which looked at sedimentary basin geothermal power and the opportunities thereof. The idea is pretty simple. There's a lot of heat in the earth, quite a lot of heat in the earth. And there's also a lot of potential to pump water into the ground to extract that heat, to draw out that heat used to generate power. So geothermal systems largely involve some kind of an injection system and some sort of an extraction system and harvest the heat that's collected in the water in the subsurface. One good bit of news on this one is if you're very interested in using geothermal and coupling it with other sources of non-CO2 generating systems, well, you can always use this as a part of your CO2 sequestration system and simply use CO2 as the working fluid instead of water. Okay, so what is SED-HEAT? SED-HEAT was a system that was set up a long time ago. It's a research coordination network. I wrote the principal grant, but there were also several members of this, totally about 300 of us that were looking into this topic of geothermal energy and how to harvest sedimentary heat from sedimentary basins. And so our goal to form a central point of unity, exchange, and education to exceed the science and engineering challenges of sedimentary basin geothermal. Well, this was involved a lot of different organizations, but it was funded by the National Science Foundation. We held a whole bunch of meetings. So what did we do? We had 4 large conferences, about 12 incubator conferences. We published, we wrote some grants, and we got together and talked about this topic quite a lot and explored the ideas and the potentials. We were focused on sedimentary basin geothermal and what kind of potential sedimentary basins had for extracting geothermal heat. And so there were lots of people involved with this in lots of different categories. So we had engineers, we had science society people, we had economists, we had various geologists, we had chemists. My particular role, I work with sedimentary basin architecture and the way sedimentary deposits are laid down. And the purpose of trying to understand how water flows these sedimentary systems. So functionally, I'm a plumber. Okay, so why bother looking at sedimentary basin geothermal? Well, there's reasons. Here's the first, is that geothermal energy has a role in the renewables world and as a major power source for the nation and for the world. We are all very keenly aware of the issues with CO2 in the atmosphere and what fossil fuels generate. And fossil fuels have been a very useful source of energy for us for a long time, but we understand that we need to be looking at some other ways of generating power that don't produce large amounts of CO2. So far, wind and solar have been the main areas where we've tried to address this problem. Of course, the problem with those is that they're intermediate. In the case of geothermal, it's base load. It generates steady power. So it has a tremendous advantage in that you can use geothermal, you can ramp it up, you can slow it down, you can keep it steady, and you can keep providing power at all times, which is a very, very important thing in any energy source, as essentially we don't handle power surges on the grid very well in this modern computer-based age. Okay, so how much energy are we talking about? Well, the total amount of energy in the continental crust is vast. We've been exploiting this one at the top in fossil fuels. But if you look at the other sources of energy, of course, fissional material, one day maybe we'll have that. We don't really have the power of the sun on Earth safely just yet. But what we do have is a huge amount of heat stored in the planet is geothermal energy. Largely in the continental crust, the bulk of that energy is going to be in basement rocks. And so that's what it generally goes as hot, dry rocks. So there's been a large geothermal movement to try to harvest the heat in hot, dry rocks. So the principle there is very simple. You drill a hole, you drill another hole, maybe another hole, but you inject in one hole, you extract in the others. Problem is, of course, there's not a lot of porosity in basement rocks. So what you do is you frack it. You frack it severely, make lots of fractures, and the idea is that you can generate pathways from the injection wells to the extraction wells and harvest the heat in the subsurface this way by generating your own porosity. In theory, that works very well. There's virtually limitless amounts of heat energy down there, and it's going to be one day a fantastic way to generate heat, and it will solve a lot of problems for us. For right now, though, we do have one pretty serious problem with it. It's called thermal breakthrough. You generate lots of fractures, and so what will happen is the water will simply find the fractures that are most preferable for moving water. Then, of course, the water moves through there, harvest the heat from around those fractures, which makes the rocks contract, which makes the crack bigger, which makes even more water flow through there. And eventually, after a while, all you're doing is pumping cold water in and pumping cold water out, and you're not getting the results you wanted. So we haven't quite cracked that egg just yet. One day we will, and then we'll all be drilling holes down into basement rock. Sedimentary basin geothermal takes another approach. It says, well, you already have porosity down there. You already have pathways for fluid. You can enhance them like enhanced geothermal by fracturing, but you don't have to deal with this thermal breakthrough problem as much simply because you can disperse the fluids through existing porosity in the rocks. Okay, so how much heat are we talking about? Well, there's a lot of heat down there. And of course, most of it's in basement rocks. That said, there's plenty of it in sedimentary rocks. So we have about 100,000 exajoules as a resource estimate of heat in the continental crust under just the United States. So for perspective, the United States uses roughly 100 exajoules a year. So that's roughly 1,000 years worth of power just in the sedimentary basins. Well, geothermal up to now was run on this principle of hot rock with very hot circulating fluids generating large amounts of power. Tiffany's kind of model. So very rich, very good resources, but very local and very rare. Whereas the sed heat model is more the Walmart model. It isn't as intense a heat, but we have a lot of it. Well, the question always comes up with these sorts of things, what's economical? Well, we're going to learn that there's a lot to the economics of this, and there's a lot of ways you can approach this problem and make geothermal more or less economical, depending on how you choose to use it and how you choose to exploit it and how you choose to harvest it. That said, though, there is a number that is used quite a lot. It's 150 degree Celsius water pumped at about a half a barrel a second. That's good for about 3 to 5 megawatts of power. And so that's kind of where people go, okay, you're pretty safely into the positive economic world at this point. That's a lot of water. That's a lot of pump rate. That said, we've seen it before. There are wells that have pumped those kinds of rates. Okay, so where's the heat? We've got lots of heat under the United States. We've got lots of sedimentary basins, and that can be said of just about any country in the world. Okay, so why does this particular idea of sedimentary geothermal heat matter? Well, let's look at our world problem when it comes to energy generation. This is world energy usage. One thing that should stand out to you immediately is that little thin blue line in the middle, that's North America. Underneath that, that's the rest of what we call the developed world. As you can see, most all the growth in energy usage in the world has been in Asia. And then right behind them will be Africa and South America. So most all the growth going into the future, the top diagram, is going to be in that part of the world. We're pretty much flat. Actually, most of the developed Western world that has been the large users of energy in the past are slated to actually shrink in energy usage going forward. This is an example of China. As you'll note, in this case, they're about 3/4 of their energy usage is fossil fuels. So the bottom line of it is we can't address this problem with just finding something that countries that are wealthy can use, but the rest of the world can't. You may be in here listening to this talk because you want to make money off of geothermal, and you may be here because you want to address the CO2 problem with geothermal. I guess I would be telling you they're one and the same. We have to be finding an energy production method that is actually economical for the world going forward. It won't help much if it's just useful for us. Geothermal hasn't been high on that portfolio so far. Most of the renewable use in the world and most of the movement in that area is in hydropower, wind power, solar power, and geothermal's had a fairly small bite of it. There's also one other moving part in this is public perception. This is a poll of Italians. It could have been a poll of just about anywhere, but what it's telling us is this, is that people tend to trust scientists. Believe it or not, it looks like they trust energy companies a bit too. But the bottom line is that solar and wind is the areas where people are already familiar with renewables and the potential of them. Geothermal, we've got a lot of open ground there. About half the people in Italy, in this example, don't have an opinion one way or another about geothermal going forward as an energy source. But on the other hand, this can go either way. We can go towards the solar and wind and have a positive view, or you go the other way down there at the bottom. Nuclear addresses the CO2 problem too, but as you can see, most people have a pretty negative opinion of nuclear. Okay, so what did we learn in all this work with said heat? Well, first off, there are three areas that I want to talk to you about in terms of geothermal potential. Potential for use of geothermal energy on the grid, potential for geothermal energy for use as direct heat, and as energy storage as battery. That's a big one, I think, going forward. Let's start with the grid. This is a place where we're most familiar with the idea of energy usage. So most of the plants that we think of in geothermal energy usage are places like the geysers. We have three, for instance, large plants in the US that generate power on the several hundred megawatt scales. So the geysers is one of those, and it uses very hot circulating liquids. In the world, the total amount of capacity that we have is about 125 gigawatts of power in the world for generation of electricity using geothermal energy. Just as a note here, it's always good time for a physics lesson, but for a quick one right in here, when you're talking about we'll talk in terms of joules, watts, gigawatts, lots of things, but a joule is the power to move 1 kilogram, 1 meter, and 1 second. Watts is how many of those you're doing each second. So a gigawatt, so when we talk about power, it's usually in kilowatts, that's 1,000 watts. When we generate power, we often talk in megawatts, that's 1,000,000 watts, and gigawatts is 1,000,000,000 watts. A terawatt is 1,000,000,000,000 watts. And so the US capacity for electricity generation is about 1 terawatt. A typical nuclear reactor is about 1 gigawatt. Okay, so with that out of the way, let's look here at how we use energy in the United States. Again, we're up to about 11% renewables in terms of our total energy usage. That breaks down heavily with biomass, wind, solar, hydro is the ones you might expect. Again, geothermal, we haven't exercised our full potential in geothermal. So one way to look at that is the field is wide open to us. If you want to make a difference in geothermal, there's a lot of opportunity out there and a lot of things that can be moved out of the way to make for more power usage by geothermal. So there's a lot of market capacity here. Okay, so what do we do with all this power? Well, first off, we use it largely for residential, about 11%, commercial, about 10%, industrial, about 25%, and transportation, about 25%. And so what that means is in terms of our total energy usage in the United States, most of the electricity we're using is going to residential, commercial, and industrial purposes. Most of the petroleum is going obviously to transportation and some to industrial purposes. Very little to things that are used for electricity. Okay, so with geothermal, what are our challenges and what are our hurdles? Well, we've got to drill holes in the ground. One of the things about geothermal, of course, is that when you drill a hole in the ground and you extract the fluid, you're expecting to extract oil and gas, and the power per unit of fluid is demonstrably higher. Of course, for petroleum, hot water doesn't have quite the power in it as a gallon of petroleum. So what that means then is that you pump a lot of water out of the ground to generate the kind of powers that we're talking about. And of course, it takes a lot to drill a well, so you don't want to miss. Good news about this is that when we think about petroleum, we often think in terms of source, migration, reservoir, and trap. In geothermal, it's a little simpler. You got two to worry about: heat and water. You want heat in the ground and you want water as a vehicle to extract it. As I mentioned, though, you can replace that water with other fluids, CO2 being a big one. Okay, so first off, in the petroleum world, nobody in their right mind is talking about pumping a half a barrel of water out of the ground on purpose. That said, though, we pump at those kinds of rates into the ground on purpose all the time in wastewater injection wells. So we know we can do it. Okay, so what's one of our hazards that we got to think about with this? Well, one of the problems that we need to be upfront about and be watching for is this issue of seismicity and induced seismicity. We learned that the hard way with wastewater injection. If you pump too much water into the ground too fast, you can actually trigger earthquakes. So let me introduce you to the Basel catastrophe. They started a geothermal plant up in Basel in northern Switzerland. And sure enough, the moment that they started this system and started to flip it on, they generated about a 3.4 magnitude earthquake, cost about $9 million worth of damage. Quite unfortunately, Basel was completely destroyed by an earthquake in 1356, and this lives in the cultural memory. So what happened, of course, is after this, people got a little scared. This virtually shut down geothermal development in Europe for a couple years. That said, there's been court cases on this. The person who ran the geothermal plant lost, but what was found was the problem is, again, tried to do too much at once. Tried to frack the entire volume early on with a lot of pressure. It triggered earthquakes. Switzerland has been moving forward with geothermal, but now they're using staged fracks, which is a little more what we're accustomed to. Okay, so we do know this about injecting water into the ground. When from wastewater injection, we've learned that when you start pumping water into the ground at the scale of tenths of a barrel per second, you can generate seismicity, both in timing and location of the injection wells. Okay, that said, this isn't something that stops us in geothermal. This is just one of those things we need to have our feelers out and be aware that we do not need that public relations disaster they got in Basel. Going forward, we need to be conscious of what we're doing. The good news for us is simple. We're not just pumping water into the ground in large volumes and just overpressuring the subsurface and leaving it there. We're also extracting water. So in the case of geothermal, you're setting up a balanced system of injection and extraction. You just have to be cognizant that this is a potential hazard. You've got to make sure that you keep your balances and plans right. Okay, so the water problem isn't as much of a problem as we originally thought. We can extract and pump water into the ground at these rates. The other resource is the heat. Well, heat's not a problem. We've got lots and lots of heat, as I explained before, especially over here in the West. So, of course, as you might imagine, most of the existing electric geothermal plants are out west, where the pickings are a little easier. Okay, we have sedimentary basins, though, all over the country. So any number of sedimentary basins could be used as an area to harvest heat. They're not just out west. One of the things with sedimentary basins, though, that we're very aware of is that they're not extremely hot. So the high heat levels you expect in basement and some volcanic areas is not typical of sedimentary basins. Of course, for us, the oil window is ending about 150 degrees C, where the pickings for geothermal is just getting good. Okay, so we have lots of basins and we have a lot of heat, but we need some sort of a geothermal system that is able to extract heat at lower temperatures. So Here's how geothermal is usually run through the turbine. Dry steam, flash steam, and binary cycles. In dry steam, you pump the water out of the ground. It comes out superheated the minute it's depressurized and meets atmospheric pressures. It's already at like 300 degrees C, so it simply flashes to steam automatically. You run it through the turbine, turn the turbine, generate electricity. The flash steam, you bring it up as water, open it into a lower pressure chamber and force it to flash with that, and that runs through the turbine. In the low heat Challenger, that's the binary or the rank binary cycles, in which case you use a separate working fluid than the water that volatilizes at a lower temperature. So how do they work? Well, flash and dry steam usually work at areas above about 350 degrees Fahrenheit, whereas binary systems run best about 200 degrees Fahrenheit to about 300 degrees Fahrenheit, or about 95, 100 degrees Celsius to about 145, 150 degrees Celsius. Basically, the oil and gas window. Okay, so how do these binary systems work? That's usually what are the most attractive approaches for sedimentary basins. In that case, you're pumping water out of the ground that is pumping out of the ground at temperatures at 100 to 150 up to 200 degrees Celsius maybe. But you're pumping the water through the ground and is sending it through a heat exchanger, which simply connects to another working fluid that volatilizes lower temperatures. So butanes and pentanes are the favorites very often, but there's some kind of organic fluid. They vaporize, they run through the turbine. And so the water's never actually, water coming out of the ground this is going through a closed loop and it never actually enters the turbine. Okay, so the economics once again. There's two things I should say that stand to reason is the hotter your water is, the less wells and less water you're going to have to pump to get the same kilowatt hours out of it. Likewise, the deeper the well, the more expensive. So there's optimal drilling depths that control the economics and optimal temperatures. So when you're running around deciding what are the economics on this system, you're going to be balancing the two when you go in. But there's lots of combinations that might potentially work in a sedimentary basin. So above 200 degrees Fahrenheit, we're running binary Rankine cycle turbines. We've got 1,700 wells like that already in Texas. They're all over the United States. So we have a lot of opportunity there. If you're interested in this reworking wells idea, I might point you to Southern Methodist University. They've been working on this idea for a long time. They'd be great partners for you. Okay. Excuse me. So what do we pay for power? Well, this is just sort of a snapshot of what people pay for power. On average, we pay about 10 cents per kilowatt hour. So by 1,000 watts of power in an hour, you're paying about 10 cents. It's a little higher if you're on the West Coast, a little higher if you're on the East Coast, a little higher if you're in Hawaii or Alaska. So nothing that's too surprising there if you've paid an electric bill. The good news in terms of installing geothermal, when you compare it to the other energy sources, other alternative energy sources, geothermal is actually quite competitive at the cost. One of the things that, of course, was a learning thing for me when I got into this, being somebody who largely wonders why one sandstone connects to another, is to get in this issue of the power purchase agreement. The way we purchase our power on the consumer side is, well, we use X amount of power and then we pay for so many kilowatt hours and we're used to that. But if you're trying to set up a plant, you generally operate under the power purchase agreement. Here in this situation, what you're doing is you're approaching some utility or some group. Google even has one, a company could do it. But you're approaching some sort of a group and simply say, I'm going to produce so much power for you at such and such cost. Basically, you're now hooked into that whether they are buying that power off you, whether they use it or not. So generally, these contracts are arranged up front for X amount of power produced at X amount of cost by such and such generator. So geothermal, Rankine cycle engines, this is just one I pulled out. It's a green machine. This will mount on a truck. They'll deliver it to your well site for you. but they'll generate power easily in the 10 cents per kilowatt hour range, and it's getting better. So the thing is that a lot of the power purchase agreement and a lot of that money you're paying for power isn't power, it's transmission and it's taxes, it's other sources. So what's going to happen with geothermal is we're just getting to the place where sedimentary basin geothermal is getting at the economic range. So we're getting down in. So the way I like to put it is when we started looking at geothermal and sedimentary basin, we were talking maybe for dollars to now certainly for pennies. So we know we're starting to get into the world where if you do this right, the economic things are just getting to the place where they're economical. So that said, we haven't taken off with it. We're just really to the place where it's a good jumping off point to make electric power from sedimentary basins actually function. So the first plants need to go in. The first planning, right now, we're not heavily on the radar. You guys can change that. Okay, direct heat. Okay, so there's a couple ways we can use geothermal power. One is we can pull the heat out of the ground and turn it to electricity. The other way we could do is just simply use the heat directly and not worry about converting electricity. That heat is energy already. Well, guess what? For building heating and cooling, water heating, that's at temperatures of like 100 °F up to about 250 degrees Fahrenheit, or like about 38 C to about 121 C. The thing is that's the temperatures the water's already coming out of the ground, maybe even a little hotter. So the thing is if you just simply use that heat directly for these purposes, you don't have to worry about losing energy in some conversion. Who's doing that? And what are they doing? Well, most of the energy usage by direct heat is being used to power heat pumps. And of course, the heat pump simply hooks into the heat source and uses that to generate heat, which is used for space heating or water or whatever other purposes. Some of it is used directly for space heating, just run the hot water or the cool water through the building like an old-fashioned radiator. But it's also used to heat swimming pools, it's used for agriculture, lots of different options. Probably won't surprise you to find that over 2/3 of the direct heat energy usage in the world is by China. For us, well, here's something that's useful to know is that if you look at things like space heating, air conditioning, water heating, the things that you can use geothermal power for, that's 2/3 to 3/4 of the energy you use in your house and also in most commercial buildings, and accounts for about a quarter of all electricity use. So clearly, if you can do this, the way I say it, electron saved is electron earned. You're not generating electricity and then using it for these purposes. You're just using the heat energy for these purposes directly. And of course, at the household and the building scale, this has caught on quite a lot. So there's a lot of homes that use geothermal heat pumps to heat and cool their house. There's no reason whatsoever that can't be done on much, much larger scales with much larger wells for larger municipal type systems or larger institutional type structures, and that you could simply sell the hot water that you're pumping out of the ground. Universities have been set up with these physical plants and steam tunnels and so forth for a long time. Places like Indiana University and Cornell University have been looking at converting to geothermal for some time and have been making steps in that direction. Okay, you can also coalesce or cascade these type systems. So you can use your direct heat in combination with power generation. So this is an example of Iceland's famous Blue Lagoon system, where they're using dry and wet steam energy from geothermal to generate electricity. Well, the water, when they're done with the flash steam, is still very hot. They simply use that to direct heating of homes, run it on to spas and run it on to agriculture, and they simply cascade. So they milk the last calorie of heat out of that water. These systems can also be coupled, and you can use your oil field injections and simply be pumping hot water out of the ground to use your injection systems and then selling the excess heat municipally. Iceland's the reigning champs at this. As you can see, in terms of heating and cooling their homes, they have largely converted to almost entirely geothermal over the years. Lastly, I want to talk about this opportunity. This is the energy storage opportunity, or earth battery as we call it. This is a big one, I think, and it's going to be one of the biggest ones, I think, biggest openings for us, I think, going forward. The idea is not completely new. Again, there's been a lot more of this that's done on the household scale. The idea is you pump hot water into the ground in the summer when it's hot, and you extract in the winter when you need it, and vice versa. There's places that have done this. Of course, they're up to almost 25,000 permits for this a year in the Netherlands. So people are doing it at small scales already. Well, why not do it at big scales? The idea is simple. Binary plants you're already running at the temperatures of binary plants when you're looking in the subsurface. Why not spike that heat a little bit? And now you're in the world of flash steam. So that's much more economical at this point. You harvest, again, think about the economics. The hotter that water is, the more heat it has, the more energy you're extracting, the less it costs to install this system. So if you could heat the water before you put it into the ground, the idea is simple. You heat the water, you extract the heat. So it would work something like this. You take your typical subsurface system in a sedimentary basin that's pumping water. Well, typical injection temperatures are usually in the 100 degrees C area. So basically set up something like, for instance, a thermal tower solar system. These things can heat water to 900 degrees. We don't need metamorphism down there. But the point is that you can generate a lot of heat this way, easily, efficiently heat your water to whatever temperature you see fit, pump it into the ground. And now what you're doing is you're spiking the temperature of the groundwater, and then you're extracting the hot water. So in this case, what you've done is you've generated solar baseload. What you're pumping and you're extracting is the excess solar heat in the subsurface that you pumped in earlier, and you're just basically pulling it out when you want it, not just when the sun shines, at whatever rate. Because one of the beauties of geothermal systems is there's about a 40% variation that you can purposely do. You can simply turn your wells on higher, and you can ramp up the amount of heat energy that you're generating, the amount of electricity you're generating, for instance, at will. And then you can turn it back down in lower peak areas. So this is a very, very, very valuable trait on the grid, because we constantly have the problem if you can't turn up and down a nuclear reactor. It's hard to do it on a coal plant. Gas plants are about the only thing that we can effectively do that with. Okay, so why does this matter? Well, if you think about the return of this, well, again, we're loaded with wells. We already know of a lot of wells that are operating in the 200 degrees Fahrenheit range. So if you spike the temperature in there, say 150 degrees Fahrenheit, and you end up over here in the world where you're starting to talk about 300 degrees C type water and so forth out of the ground, you aren't just actually pumping twice the energy out of the ground now. You're pumping about 7.5 times the energy out of the ground. So these systems, you get an exponential payback for this particular process as you increase the heat. Right now, as far as I know, nobody's actually doing this. This is an idea that we're working on. This is what the academic community is playing with. We're running models on this. We're toying with this idea. It's got lots of potential, but it needs a Mitchell. It needs somebody who's willing to take the steps to actually say, we've got all this technology, let's make it work, let's try it out, let's get it going. The closest thing is things like the Stillwell plant here, where they are coupling thermal, solar, and geothermal plants. But what they're doing is they're heating the water after it comes out of the ground and spiking the heat, spiking the geothermal heat with a little solar heat to get that extra energy boost out of it. But again, what we're saying is simple. Pump that heat into the ground and then pump it out when you want. So why does it matter? Well, let me introduce you to the duck. This is California's problem. They are moving rapidly towards solar energy, and that's a good thing. Solar does generate lots and lots of power, and we know the sun has lots of power. Solar energy would provide all of our needs. The problem is it's intermittent. So why does that matter? Again, here's the duck I was mentioning. It's called the duck curve because it's shaped like a duck. But the top the top boundary and the top line is the line that depicts the amount of energy usage per day in California. And as you might imagine, it starts off a little low. You get up in the morning, you make some toast, you go to work, it picks up through the day. We use a lot of power, but peak demand is actually in the evenings when everybody comes home and starts drying clothes or whatever. So at the same time, what's happening is the sun is coming up and generating a solar spike of power in the middle of the day. That means you have to power down all the other energy sources. So all of your other conventional power sources are depicted by the green curve. They have to be powered down during the day. What that means is after the sun goes down, as you move towards peak demand, you're suddenly facing about a 13 gigawatt ramp up of power in about 3 hours time. This problem is not getting better. It's getting worse. Okay, so how do they do it? Well, the way they do it is natural gas and bought power. So they import power, and also natural gas power plants are basically a jet engine on a turbine. You can flip it on and off. So, but what is happening is that even though we've bought a lot of CO2 out of the air by using solar during the day, we're losing a lot of it right back in the evening because we have to flip on all these fossil fuel systems that can ramp up the power. Other alternatives are being looked at. This is the Giga plan. This is actually Tesla built this in South Australia. It's a half a gigawatt battery, basically. As last I heard, California was talking about a gigawatt battery they were trying to build at the time. But again, battery storage is one answer. So you're talking batteries the size of football fields to get this done, and lots of them if you're going to be able to pull this off. So we need some sort of a battery solution to get rid of that problem. So why not use the earth battery system? Again, all that solar that's basically displacing the other sources and causing the duck issues during the day. Why not take that power, store it underground, use some of it, and then essentially be running the geothermal, a much more steady point that takes the spikiness out of this and keeps it a little more steady, and simply storing that heat underground. Again, I said there's people working on it. Let me introduce you to John McLennan and some of his group out at University of Utah. They run several simulations with this, running various different configurations, trying to generate systems of drilling and injection systems where we could store this heat in the ground. And this is just one of their models. The beauty of this is that they ran these scenarios in these simulations under very realistic conditions. And what they found is that after about 100 days of pumping and injecting, they were getting their heat back upwards towards 100%. So essentially, the biggest problem with using an earth battery system that would be our biggest concern is that you're generating all this heat, you're pumping it into the ground, and then it's simply just leaking off. Well, the reality is the sedimentary basins are already at heat levels that are right at the levels you want anyway. So when you're spiking the heat, you're not running into as much bleed off as you might think. So essentially, at least the math of this is saying that after you run this plant for just about 3 months, you're getting about 100% return of the energy that you're putting into the ground back out of the ground as geothermal power. So the answer to this is this looks like this might work. We could actually get that holy grail of return of renewable energies and actually have solar baseload. So this is our green opportunity. My saying is, let's give this a try. Somebody needs to step up to the mic and try this, because at this point, it's just waiting on someone to show the world it's economical, and then we'll all be doing it. So with that, thank you for your time. You've been a wonderful audience, and I appreciate you taking a moment with me and let me tell you what we've come up with about geothermal. Thank you.